Let's start. Uh, Welcome to this afternoon session on language design. Our first speaker is Ralf Jung, who's going to tell us about Stag Paratus.
Yes, thank you, and thank you everyone for coming to this talk about Stag Paratus, where we'll be speaking a bit about aliasing in Rust. For those of you that haven't heard, Rust is a very young programming language initiated by Mozilla with the goal of replacing C and C++ in at least some of the areas where those languages are still predominantly used. The unique selling point of Rust is that it combines low-level control, as we are used to in systems languages, with high-level safety guarantees in a modern functional-style language with industrial development and backing. The key mechanism through which Rust achieves to break the usual trade-off between control and safety is a sophisticated type system. And in this talk, we're going to look at how we can use the type system to achieve more than just safety. Namely, the goal is to get better optimizations and make our programs go faster. So let me talk a bit about the types that we are going to exploit for this purpose. It's Rust reference types. References in Rust come in two flavors, and both of them have strong aliasing information attached to them. On the one hand, we have mutable references that, as the name suggests, permit mutation, and at the same time, they exclude any kind of aliasing. So a mutable reference is always a unique pointer. And on the other hand, we have shared references that can indeed be shared even across thread boundaries, but that come with the extra guarantee that the memory they point to cannot be mutated by any party. This makes them much stronger than, for example, const pointers in C, where other parties could still mutate the data that this pointer points to. So this is strong aliasing information that we have in both cases, and we want the optimizer to take advantage of that. For example, in a function like this that takes two mutable references, we would like to exploit the fact that they cannot point to the same location. So that when we write 42 to one reference and write 37 through the other reference, then if we load x again at the end of the function, we know it will still contain 42, because the only way that writing to y could override what is in x is if they point to the same thing, which they can't. We can even generalize this to this test unique function here, which takes a single mutable reference, which we know has to be globally unique, and writes 42 into it, and then calls some unknown code. So, for example, you could imagine unknown function to be in some different translation unit, so that we have no way of analyzing what it is actually doing. And still, we know that when we read x again after the unknown code is done and returns back to us, that the memory must still contain 42, because unknown function would need an alias to be able to change the value that is stored in there. So this is a pretty powerful optimization, because we're looking at a situation where we have an escaped pointer not controlled by us, and we are calling unknown code, and still we get some of the strongest possible alias information that we can imagine. So here we have a great opportunity for Rust to not just be a safer language than C, but also one with better optimization potential. There's just one problem with this plan, and that is unsafe code. Unsafe code exists in Rust because sometimes you have to do things which are correct for reasons that are too clever for the compiler to understand. And so Rust offers this syntactic unsafe blocks where you can do things, and it's your own responsibility to make sure that you're not doing them wrong. The things you can do, for example, include taking an arbitrary integer, casting it to a pointer, and dereferencing that. So clearly all sorts of things could go wrong there if this is used incorrectly. Unsafe code is used at mostly at the lower ends of the Rust ecosystem, for example, when doing FFI, or when getting the last few % of performance out of a key data structure. However, to make sure that unsafe code doesn't break all of Rust's safety guarantees, the name of the game with unsafe code is safe encapsulation. So you always have to make sure, when you're writing unsafe code, that you're wrapping this into an API such that well-typed clients are protected from any possible unsafety. But still, unsafe code makes clients more powerful, and we can use that to break our optimization. So here's again the example function from before, and I'm going to turn this into a whole program by adding a main function where we have a local variable L, and we make the reference in test unique, this X reference, we make that just points to L. This program is still fine. We would print 42, but now we will add some nasty bits to it. So first we add a global variable, alias. Its type, *mut I32, is that of a raw pointer. Raw pointers are a bit like the dark evil twins of references, and they're not checked by Rust static checks. You can only use them in unsafe code. And then in the main function, we set things up so that the global pointer that we have also points to the same local variable as x. So now we have x and L, both x and alias, both pointing to the same thing. And so some of you probably guessed it, the next thing we're going to do is we're going to implement this unknown function as using the alias to write into L, thus overwriting what is in X. So when we run this program, it prints 7. But if we do the Z optimization, we change program behavior to 42. So it's an incorrect optimization. And that's very sad. But we're not willing to give up here, because what we can do is, instead of saying that the optimization is wrong, we would like to say that the program is wrong. That may sound kind of weird, but it's actually something that these low-level languages already do, because when you write unsafe code in Rust, all of these unsafe operations that you use, they come with proof obligations, that it is your responsibility to make sure that they hold. So for example, when you use raw pointers, you have to make sure they're not null. And the compiler gets to assume that all of these proof obligations are met. So conversely, this means if any of the proof obligations is violated, you get undefined behavior, and your program might turn out to, the result of your program compilation might look a bit different from what you were expecting. So the reason this is useful is that when justifying the correctness of optimizations, you get to assume that all of these proof obligations hold. And we only have to check that the optimization is correct for programs where the proof obligations are met. So the plan for this work is to add a proof obligation there in line 9, where we are using the raw pointer, that says something along the lines of, you can't mess with the aliasing guarantees of references elsewhere in the program. And this client here is violating that proof obligation, and hence we don't have to consider it when justifying the correctness of our optimization. And that is exactly what Stag Paratus is. It's an aliasing model that defines which pointer aliases you are allowed to use when to access memory, and the goal is to make sure that mutable references are unique and that shared references are immutable. I'm calling this an aliasing model because this is pretty orthogonal to a memory model, whose job it is to tell you, when you're reading from memory, what is the value that you are getting. Stag Paratus doesn't care much about values. All it cares about is when you have many aliases, which of those are you allowed to use and in which order. Now, the design space here is pretty big, so we have to figure out what it is that we can evaluate about this to make sure that our model makes any sense. And there's kind of constraints from two sides that we're gathering here. On the one hand, we have to make sure that Stag Paratus is restrictive enough that it imposes enough proof obligations to actually justify useful optimizations. And to make sure that that is the case, we formalized Stag Paratus in Coq and proved the optimization is correct. On the other hand, we have to make sure that Stag Paratus still permits programming. We can't just rule out all programs. So we have implemented Stag Paratus in an interpreter, and then we run a body of interesting unsafe Rust code in it to make sure that that unsafe Rust code is still correct under the extra proof obligations that we are imposing on it. So to give you a basic idea of how Stag Paratus works, the key idea is that Rust already has a check that makes sure that in safe code, references behave the way they should. And this is a static check, which is called the borrow checker. With Stag Paratus, we take that static check and we turn it into something dynamic, something like these proof obligations on the actual runtime program values. And because it's dynamic, we have the extra information that we need to make those checks also apply and work with unsafe code. So to explain what the checks are, I have to first talk a bit about what the borrow checker is actually doing statically. So here's some example code. We start with a local variable, and we create a reference to that. In Rust, we call this borrowing, because in Rust, we think of local variables as owning the memory where the value is stored. So L owns the memory where 13 lies, and then A borrows from that. And then we're going to create another reference, B, by dereferencing A, and obtaining a reference again, which looks kind of like a no-op, but in Rust, this is a very meaningful operation, and we think of B as taking what A has borrowed and then borrowing that itself in turn. We are now allowed to use B to access this memory. We are allowed to use A to access that memory. But after we used A, we are not allowed to use B again. And if we do, the compiler complains about lifetimes. Lifetimes are something that gets inferred by the compiler, and it says for how long a reference may be used. In this case, the lifetime of the reference B is the shaded region here. And the constraints to which lifetimes are subject is, number one, you can only, the lifetime has to end when you're using when the original owner uses the memory again. So when I lend you something, I may only use it again after the lifetime has ended. This is why in line 5, when the original lender A gets used, the lifetime is over. At the same time, the receiver of the borrow, B, may only be used during the lifetime. Right? If I borrow you something, you can only use it while you still have it before you give it back to me. So putting these two constraints together, we have a conflict here because we cannot resolve them both at the same time. But looking at this example, there's a few things we can learn. On the one hand, we see that borrows come in some form of chain, right? There's a root here, L, which owns the base memory, and then A borrows from L, and B borrows from A, and so on. And on the other hand, the constraint that the compiler puts on us basically means that we have to use these borrows in a well-bracketed way. The thing that went wrong is when we had A, created B, then used A again, and then used B again. That was not OK. So it's probably not going to be a big surprise when I'm saying that to dynamically check the well-bracketed nature of these uses, we're going to add some form of stack. And that's why it's called stacked borrows. Concretely, stacked borrows is implemented as some kind of instrumented abstract machine that carries a bit of extra state that we use to formulate and enforce our extra proof obligations. On the one hand, references don't just come with a value that says which point of memory do they point to, but they also come with an extra tag. And the tag is used to distinguish references that point to the same thing in memory. Because as we've seen in the example here, A and B point to the same thing, and still they are different. So we have to find some way to make them different, and that is what this tag does. On the other hand, next to every location in memory, we don't just store the byte, that is the value that is stored there, but we also have a stack that consists of these tags that tracks which references are allowed to access this location. And the order in there reflects this borrow chain that I mentioned. So here, we have 0 at the bottom of the stack, and then we have 1 on top of it, and we think of the reference, that whatever reference has tag 1, as borrowing from the reference that has tag 0. So the rules that we now will add is that on the one hand, we have a new proof obligation. Whenever you're using a reference or a raw pointer, it is your obligation to ensure that the tag of that reference is still in the stack. And on the other hand, this use will also have the side effect of popping everything that is further up the stack away, because those are things whose lifetime have now ended because we performed a conflicting access. If we apply those rules to our example program, you can see that when the alias gets created, then we have a stack consisting first of else tag. I'm using the names here to not have the tag numbers because that's a bit confusing. We have a stack that consists first of else tag and then aliases tag on top of that. But then in the next line already, we're using L again, at which point everything above L will be removed from the stack and the lifetime of alias ends. Instead, we're adding X on top of L in the stack, reflecting that X borrows from L. And this means when we get to line 9, where we had the problem before, where the aliasing was violated, we now are using a pointer alias that is not in the stack. So we are violating the proof obligation. And so this is not a correct program, and we don't have to consider this program when justifying the correctness of our optimizations. OK, so this is not, of course, a proof that the optimization is correct. I would love to give you a proof sketch of this here, but they only gave me 17 minutes, so I can't. But you can find that in the paper, of course. But what I can briefly look at is what happens when we run this example code in the interpreter that we wrote. So we can just feed it that code and execute it, and then it will show an error message on exactly the line where the problem is, talking in more or less cryptic terms about the fact that you're using a pointer that has a tag that is not in the borrow stack. So to make sure that our model makes any sense, we took the Rust standard library, or in particular the parts of it which are low-level pointer manipulation and the data structures, or the platform-independent parts of it, and we run that in Miri every day to make sure that this continues to be a valid, that all of this code continuously actually matches our model. In doing so, we found 6 cases where the code did something that Stag Paratus said wasn't OK, where the code was violating the proof obligations. But all of these cases, when we reported them, were accepted as bugs by the Rust developers and have since been fixed. So now the standard library is actually clean as far as Miri and Stag Paratus are concerned. So well, that's all I got. There's, of course, a lot more things in the paper. Namely, on the one hand, we explain how shared references are handled by Stag Paratus and how we make sure that they are immutable. We also explain interior mutability, which is an interesting feature in Rust, where Stag Paratus actually sometimes can be mutated. Where shared references actually sometimes can be mutated. We also have a mechanism called protectors that lets us do some even more powerful optimizations than what I've shown so far. But of course, that doesn't mean we are done. One of the interesting pieces of future work we would like to explore is concurrency. So far, this is all sequential. We don't expect any major problems there, because in Rust, concurrency and in particular race conditions are only permitted with interior mutability. And for those, we are already very flexible. So we don't think that any of the permitted concurrency interactions in Rust should be any problem with Stag Paratus, but you never know until you try it. And on the other hand, of course, we would like to integrate Stag Paratus with Rustbelt. Rustbelt is work that we presented here at POPL 2 years ago, and it's all about formally proving that all these proof obligations are actually met. So we added some extra proof obligations. Of course, we would like to expand the proof to cover those as well. So this brings me to the end of my talk. I presented Stag Paratus, which is a dynamic model of Rust reference checker that can be used to ensure that intraprocedural type-based analysis are sound, even in the presence of unsafe code. If you want to play around with this, you can find Miri online in the official Rust playground or the distribution, and you can find more of our Rust work on the Rustbelt website. Thank you.
Okay, thanks, Ralf. We have plenty of time for questions. Are there any questions?
Thank you for this talk. Is it right that you have one stack for every reference?
No, we have one stack for every location in memory.
Yes. So you could have the ABAB rejection is not for things that refer to different memories.
Yes.
Okay.
Everything is per location.
At the beginning, you were talking about pointer to integer cast or integer to pointer casts. How would that work in this model? Because, well, pointers, there you added this nice number to it, the stack. But in the case of integers, well, they're just integers.
The model is prepared to handle the idea that some things are untagged, and it will basically treat all untagged pointers as one big equivalence class. This is in fact what we already do for raw pointers right now to kind of test that. So the idea would be that when you cast something to an integer, or currently it's when you cast something to a raw pointer, you remember in those stacks that the untagged cloud of pointers is allowed to perform a certain access, and where in the stack the untagged equivalence class lives. And then whenever you cast an integer to a pointer, you make it untagged.
Do you have any idea if that is compliant, if you would integrate this in Miri, if this would work with existing code?
I mean, the raw pointer thing, we do that in Miri already. It is untagged. Miri also implements integer pointer casts, and to the extent that the existing code uses that, it works. But it's not doing crazy things with that, I think. But like, basically, it's just considering it is an untagged pointer, and that part we have tested in Miri, so that works.
Thank you.
Right, so we have a question from Slido. Unsafe is for running efficiently. How costly is it to maintain a Stag Paratus at runtime?
Oh, I mean, Miri is slow. Miri is like 1,000 times slower than running this code for real. But this is, I mean, the Stag Paratus isn't maintained during normal Rust execution, right? This is just when you run it in Miri to test that your code conforms with the model. And then I'm sure there's things we could do, but currently we haven't optimized that for performance. But when you're just running your program normally, of course, the stack doesn't exist just like any of the other auxiliary state. You need to define your abstract language semantics.
Hi, thanks for the talk. Are you aware of any safe design patterns that are not allowed by this restriction?
I mean, safe code should all pass it, otherwise we have a problem. Because the entire premise of Rust is that if we have safe code, all the proof obligations work. And as far as we know, the safe code, I mean, the one we tested it on, works. There are some unsafe design patterns, as in unsafe code wrapped in safe APIs that are interesting. The most probably the most interesting one is so-called self-referential struct. So where you have a struct that contains a pointer to a piece of itself, which is actually a thing now in Rust with async functions, and which are compiled to stack machines, if they contain a pointer if they contain a pointer to another local variable. That is currently not compatible with Stag Paratus, because Stag Paratus, basically there's an alias going on here, because the pointer points to the entire thing again. We have some rough ideas to maybe require the compiler to mark certain types or certain pointers, or require the programmer to mark certain types or certain pointers as not actually making all of the usual uniqueness assumptions, so that we wouldn't consider them as aliasing, basically.
what about you're running it on the interpreter on the test suite? What about the test coverage? Because the test coverage will depend on the values actually. So how practically useful is that? How much coverage do you get with that kind of testing? It's proof that your technique is kind of correct, but how much do you really test with that?
I mean, we don't have any direct measurement of the test coverage, but I developed this by writing the implementation and tweaking it until on smaller test cases and then growing that until it all worked. So I'm pretty sure that at least almost all of the weird quirks that I didn't talk about, but that you can find in the paper, they are all actually exhibited, because if I take any of them away, our tests fail. So I think in terms of the weird quirks, we have pretty good coverage. I think the potential problem in terms of coverage is Rust features. There we have whatever the standard library uses, which will probably not be the latest and greatest that's just being implemented, because most of that is older code. So that's the more interesting part, I think. But Miri is also being used elsewhere. There's more and more libraries that use Miri to make sure that they are getting all of these proof obligations right. So we get some extra coverage there.